Hello everyone, I am Dr. Mohammad Saad and today we will discuss about the determination of concentration of iron in a vitamin tablet. Here is the outline of the today's presentation presented in front of you people. You can see and have a look over all the topics that we will discuss in this experiment. Let's talk about the principle which will be used in determining iron in the vitamin tablet. We all know that iron binds with orthophenethylene and produces reddish orange complex. But this complex is only made by ferrous ions, not ferric ions. Therefore, in order to convert all the ferric ions that are present in vitamin tablet, we need to use hydroquinone as a mild reducing agent. So this will form a stable colored complex, and we all know that if uh, the color is formed between iron and OPT, here's the equation which will be used in explaining the process of formation of complex between ferrous. In the first step, when we add hydroquinone into our system, all the ferric ions will be reduced into ferrous ions, and then after adding hydroquinone, we add orthophenethylene, 110 orthophenethylene, commonly known as OPT, and the OPT then binds with ferrous to form a ferroin complex that absorbs at 508 nanometer. So the more the concentration of complex, the more will be the absorbance according to the Bell-Lambert's law. So the concentration of the complex depends upon the concentration of ferrous, and the concentration of ferrous is solely dependent on the concentration of ferrous ions coming from the tablet. Therefore, we can determine iron in the vitamin tablet using this phenomenon, using this principle. So Let's start with the preparation of sample solution. In a 250 ml beaker, we will first take 12 ml water and then we will add concentrated HCl 13 ml. It will produce 6 molar HCl solution that will be required to digest our tablet. After doing so, we will put the beaker containing 6 molar HCl on a hot plate stirrer and then carefully add the vitamin tablet into it. After adding vitamin tablet into it, we will cover the beaker with a watch glass to prevent any splashing or to prevent excessive evaporation. It will take about 20 to 25 minutes for the tablet to be digested, and after digestion, the content of the beaker uh, is filtered into a 100 ml volumetric flask which is termed as flask A. The content is quantitatively transferred into flask A. It means that whatever content is there in your beaker, in the digestion beaker, transfer all that content into a flask using a funnel having a good filter paper, and then when you have transferred all the content, add some water into the beaker and swirl it so that if any ferrous ions or ferric ions would be attached on the walls of the beaker, they get dissolved in the water, and then pour the same water onto the same filter paper that was used to filter the content, the digestion content, so that we can get each and every ion of iron coming from the vitamin tablet. And then ultimately you need to make up the volume of that 100 ml volumetric flask. This flask will be termed as flask A. You should label it as flask A by your permanent markers, and then take 10 ml of a liquid and 10 ml solution from flask A and make up into another 100 ml volumetric flask. This will be called flask B. Okay, now you can take 5 ml from this flask B into another 100 ml volumetric flask. This is termed as flask C, and now you need to wait because you have to determine the amount, the volume of sodium citrate added into this flask C. So after adding only 5 ml of this flask B solution into flask C, you need you need to wait, because you will be determining how much sodium citrate would be needed in flask C. You need to stop yourself here. Now the next critical part is the adjustment of pH. The complex between iron and OPT can be formed in a range of 3.0 pH to 4.5, and the best pH, the optimum pH for this complex is 3.5. So we will achieve this pH of 3.5 by adding sodium citrate into our system. Because sodium citrate is a base, we know that. So what it does, it masks other interfering ions such as copper, zinc, calcium, because these ions could also bind with OPT and reduce its concentration and interfere with our analysis. And pH adjustment is very important, as we have already discussed, that it is used to adjust pH to 3.5, because if our pH is not 3.5, let's say it's 2, then complexation is incomplete, because uh, some of the iron would be found in 3 plus state, and if the pH goes beyond 6, then the precipitation occurs in form of ferrous hydroxides. So it is very important to adjust your solution pH to 3.5 using trisodium citrate. Now, these are the reagents that you will be needing in your experiment. We will give you iron standard having an approximate concentration around this. You can find this accurate concentration on the volumetric flask on the day of your performance. We will need trisodium citrate, then hydroquinone, then orthophenethylamine, and all these things. Okay, so you can see the role, and you can see what each and every reagent does in your experiment. Now, how to add sodium citrate into your system? We will be noting down two volumes of sodium citrate, one for standard and the other is for sample flask B. Now we first discuss it for iron standard. Uh, the iron standard is given to you from a volumetric flask. You can collect it in a beaker, and then you can take 10 ml by pipette of that iron standard, and you dip pH electrode into it. When you dip pH electrode into it, we make it in a acidic solution. So the pH of that iron standard would be around 1.5 to 2.0. When you add sodium citrate, trisodium citrate from your burette, and stir the solution, the pH would go up, because trisodium citrate is a base. So when the pH reaches to 3.5, you stop the addition of trisodium citrate and note down how much trisodium citrate volume was added into the system. You can name it as V1. Now, as you have already prepared sample flask B, you take 10 ml liquid from sample flask B and dip pH electrode into it. Because there was so much acid into the solution, because we digested the tablet in 6 molar HCl, so the pH would be around 1.5 to 2. When you add trisodium citrate and the system pH reaches to 3.5, you note down the volume, and now you can term this volume as V2. V2 means the volume which was required to reach pH 3.5 of the sample flask B. This slide shows you how to prepare your reagent blank and the standards that will be used to determine the concentration of iron in your vitamin tablet. In your 50 ml volumetric flasks, if you are going to make blank, so you will not be needing any iron, so you do not add any iron stranded into blank. And when you want standard number 1, you add 1 ml of iron standard, and then 2.5 ml, then 5.0 ml, and then 7.0 ml of the iron standard that will be given to you on the day of performance. Now the volume of trisodium citrate will be added in a proportional manner. So this proportional volume of trisodium citrate is very critical because each standard has a different volume of acidic iron solution. This contains 1 ml of iron solution, this contains 2.5 ml of iron solution, this contains 5 ml of iron solution, and this contains 7 ml of iron solution. So we cannot add similar volume of trisodium citrate to all these flasks because we need to manage the pH to 3.5, so we will be needing a proportional volume. Okay, so this proportional volume will be calculated based on the V1 that we discussed in the last slide. The V1 will be multiplied by 1.0 ml, the standard that you are going to make, and because the V1 value was calculated for 10 ml, so this 10 would remain the same. The only thing that changes is the volume of your standard solution. If you are working for 2.5 ml iron standard, then you need to multiply V1 by 2.5 and then divide it by 10. So all these factors would remain the same apart from the volume that was added for iron standard. And then by doing so, uh, the condition is now set up to add hydroquinone, then OPT, and then you can make up the volume of the standard to 50 ml. This is the procedure for color development. As we have discussed, you need to transfer the liquid sample or standard into the labeled volumetric flasks. Add the proportional volume of trisodium citrate solution, and then you need to swivel your flasks so that all the content gets homogenized. Then add 1 ml of freshly prepared hydroquinone solution using a measuring cylinder in the reagent blank flask and all the standards. Mix and wait for about 2-3 minutes to ensure complete reduction of ferric into ferrous. Then you will be needing 1.5 ml of 110 orthophenolphthalein solution by measuring cylinder in reagent blank and all standards. The orange red color will be visible very immediately, and because the sample flask C is of 100 ml, twice that of the volume of the standard, therefore you need to double the quantity, double the volume of hydroquinone and OPT. So in flask C, in which you have already taken 5 ml of a liquid from flask B, in that 5 ml you need to add 2 ml of freshly prepared hydroquinone, and then after waiting for 2 minutes you need to add 3 ml of 110 orthophenolphthalein. And when you add 3 ml of OPT, then you observe that an orange red color will immediately be observed. After doing all these things, you need to make up the volume of all the volumetric flasks, and then you need to wait for about 10 to 15 minutes for maximum complexation. Then you have a reagent blank, you have 4 standards, and now you have one sample flask C. Measure the absorbance at 508 nanometer for all the solutions using reagent blank as your blank. When you have taken all the observations, then you need to make a graph, a calibration curve, in which x-axis would contain the concentration of iron as milligram per ml or microgram per ml, whichever is suitable and easy for you, and on y-axis you put absorbance. So this plot should pass through origin, and if it is not passing through origin, it is not a big deal. It is only uh, that you have not prepared your blank accurately. Now if you have prepared your graph, which means calibration curve, then the absorbance of your solution could be plotted on the graph, so that, for example, if I show you the graph here, here is the concentration part and here is the absorbance part, and when you plot your concentration and absorbance plot, it comes out as a straight line. Suppose that your absorbance of flask C, sample flask C, comes here, then you need to draw a perpendicular, and this portion, this will be giving you the concentration of iron in your sample flask C. You need to convert this concentration of iron in sample flask C into the milligram of iron in your tablet. How you would do this? It can be done by using this formula. Suppose that you have a concentration of 0.006 milligram per ml. Because the concentration is in flask C, you need to multiply it with the volume ratio, because the flask C was prepared by taking only 5 ml liquid from flask B and dilute into 100 ml. So this volume factor will give you the concentration of iron in flask B. And because flask B was prepared by taking 10 ml from flask A and diluting it to 100 ml, so this multiply or this volume factor will give you the concentration of iron in flask A. And because flask A was prepared, flask A contains all the irons from tablet, and it was of 100 ml. So concentration whenever gets multiplied with volume will give you the amount. So because the flask was of 100 ml, so we need to multiply it with the concentration, so we will multiply it with 100 ml. So all these factors, all these dimensions get cancelled out, milliliter to milliliter, milliliter to milliliter, and this milliliter will be cancelled out with this milliliter, and finally you will get only what? Milligrams. These are the milligrams of iron that were provided by the iron tablet in your system by digestion. Once you have determined how much iron was released by your vitamin tablet, you can compare it with the company label claim. This is the formula that is used to determine the percentage of label claim. You put your experimental value on the top and you put the claim, the company label claim here, and you need to multiply it with 100%. Technically, the percentage should be closer to 100%. But if it is more than 95%, it is quite acceptable. Anything less than 95% is solely not acceptable. When you perform this experiment, these are the expected results. The calibration curve should have a regression coefficient of greater than 0.995, which is almost desirable. Uh, you will study it in your upcoming lectures in analytical chemistry, that how this regression coefficient is calculated. For the sake of simplicity, let me tell you that all the data points, if all the data points are fit on a straight line, then the R square is closer to 1. So anything that is greater than 0.995 is quite acceptable. And because we know that Beer-Lambert law directs that the calibration curve should pass through origin or through 0 when you have uh, a good region blank. But if it is not passing through 0, then the analysis is acceptable. The only factor is that you have not prepared an appropriate region blank. The iron OPT complex is quite stable if it is protected from sunlight, because sunlight disintegrates the complex and therefore the color diminishes. The precautions that are needed in this experiment is the excess hydroquinone, because hydroquinone itself produces a slight yellow color, so it is used in appropriate quantity. Metals such as cobalt, copper or zinc should be masked, and they do not need to interfere. They need to be masked by citrate, adding citrate appropriately. Phosphate can also precipitate iron 3. It is avoided by keeping iron reduced and pH controlled. The advantages of this method is it is simple, because it requires only spectrophotometer and does not need any HPLC or any sophisticated instrumentation. It is sensitive, which means any smaller change in concentration will produce a significant change in the spectroscopic signal. It is selective because iron binds selectively with OPT, and it is stable, which means that you can reproduce your results a number of times. The only disadvantage being that it requires a careful pH control, and because hydroquinone gets oxidized, so it needs to be prepared freshly. Thank you for your time, students. If you want to know about my research expertise and my research publications, you can scan this and follow the link that will lead you to my Google Scholar research profile. Thank you so much. That's it for today.